this is you and I, the human body, our skin, all our internal organs behind us, underneath it all. And essentially it's all made up of atoms: oxygen, carbon, hydrogen, nitrogen, phosphorus, sulfur, and so on. All these essential elements that go to make us up. And then there's the inside, all our musculature. We need sodium, potassium, chlorine, magnesium for our muscles and nerves to activate and so on. Calcium we need for our bones. We need iron for our circulation, for hemoglobin to transport oxygen around the body. So we're pretty reliant upon a lot of these elements. And of course, don't forget your jewellery. Who's this guy? Yeah, absolutely. The very famous American astronomer and science communicator, Carl Sagan. And his many quotes. I put a few in the handout. We are made of star stuff. And was he right? Yeah, let's find out. That's why today's talk is the origin of the elements, the making of everything from us to gold. Also known as nucleosynthesis, but that's more of a boring term. There's a lot of information we're going to be talking about tonight, and that's why you've got all the handout. So in the luxury of a handout, of course, you can expand on stuff. So I hope you do read the handout and enjoy it. Okay, so you've probably seen this before. This is the periodic table, but it's color-coded to allow for the origin of all the different elements. And it's been around on the internet now for some time, so you're probably familiar with them. And there's 118 elements there, most of them made by nature, some man-made. So tonight we're going to explore each mechanism that's involved in forging all of these elements. These are the chapters or sections I've broken it down to. We're going to start off with an introduction about atoms, particles, and principles. Arguably, that's the most important section. We're going to talk about the principles of building up elements. Then we'll talk about the Big Bang, dying low-mass stars. We'll talk about exploding white dwarfs, exploding massive stars, merging neutron stars, and cosmic ray fission. And then we'll have questions afterwards. Okay, so let's talk about atoms, particles, and principles. Like I said, this is the most important part of it all. You're probably familiar from high school, some of the basic stuff off an atom here. We've got this central nucleus, and the nucleus is made up of neutrons, which have no charge, represented in green here. Then red protons, which are represented there in red, and they're positively charged, and it's them that determine the chemical properties and determine the relevant element. And then represented in this colour, you've got electrons, which are negatively charged particles in sort of orbits around the central nucleus. Just a little bit about atoms are very, very small. But just putting it in perspective, if you would get an atom into, say, a massive, huge cathedral with all the electrons filling up the entire cathedral, the nucleus would be a cube of sugar sitting on the floor. Just puts everything in perspective. So most of us are actually thin air, just almost everything, atoms. And that nucleus is so tiny, but it's the nucleus that contains that proton that determines the chemical properties. So it's the nucleus of an atom that really is the important part, and that we're going to be focusing on tonight, building up of the nuclei. So protons and neutrons, they are made up of elementary particles called quarks. And quarks can be up quarks or down quarks. The proton has got 2 up quarks and a down quark, and the neutron 1 up and 2 down. They are held together by what we call the strong nuclear force, and that's mediated by particles called gluons. And it is the strong nuclear force, and this is important because this is going to come up a lot of times throughout the talk. The strong nuclear force is what not only holds quarks together, but also holds the protons and neutrons together. Because you've probably picked up there, these protons are positively charged, and we all know with electromagnetic force, light particles tend to want to move apart, but it's those strong nuclear force, those gluons, that keep them together in one point. The other point here is that that strong nuclear force is a short range only. It can only operate within a relatively short range. That has huge implications for what we're about to talk about. Okay, so as mentioned, it's the number of proteins that determines the element and its chemical properties. And we've just got a picture here. This is of some helium with 2 neutrons and 2 protons in the middle and 2 electrons around the outside to create a neutral helium. And I just introduced every element here's got a abbreviation, He for helium. And you'll see 2 numbers. You'll see a top one known as the mass number, and that's usually the total of protons and neutrons, and the atomic number down below, which is the number of protons. If you change the number of protons in a nucleus, you're actually changing the element. If you're changing just the neutrons but keeping the protons the same, it's the same element, but you're just creating what they call a different isotope. And you'll see that name will come up a few times as well. Another little, I'm getting all the basic stuff done now. So a hydrogen nucleus, you probably use the word hydrogen all the time, quite frequently, is just one single protein, proton. One single proton is a hydrogen nucleus, and it's in the neutral state, it's got 1 electron around it. It does have isotopes with 1 and 2 neutrons respectively for deuterium and tritium. Okay, now a helium nucleus, and that's the next one that's going to come up time and time again, that's worth us talking about. A helium nucleus has 2 protons and 2 neutrons. There it is as there, up, sitting right there, 2 neutrons and 2 protons. That's a helium nucleus. It is also known as an alpha particle, because the name alpha particle is going to come up frequently through this talk. So when we talk about an alpha particle, it's just a helium nucleus of 2 protons and 2 neutrons. So it's nice just to get this terminology right up front. So that's a little bit about atoms. Let's now talk about some principles of particle capture. And that's what it's all about. It's partially about capturing particles to build things up. And I want to talk about these 3 main types here. Proton captures, neutron captures. We're going to break that into a slow S process and an R rapid process, and then alpha capture. So proton capture essentially refers to a form of nuclear fusion, where you get 2 protons, positively charged, but you give enough energy, temperature and pressure, you bring them together and you create helium. And it's quite a process, which we'll go into a little bit more depth shortly, but essentially you're bringing hydrogen together to form helium. There's 2 ways that can be done, through what they call the proton-proton chain and the CNO cycle. I go into that a little bit more depth with the handout, but needless to say, there's 2 main pathways that you can go hydrogen to helium. You need temperatures of at least 10 million degrees to be able to do that, to bring 2 protons together and initiate some nuclear fusion, or proton capture. In other words, bring 2 protons together to create a helium. Then there's neutron capture. Neutrons capture refers to when you get a larger nucleus, such as here, and a neutron is going by and you may manage to capture it to make a larger nucleus there with an extra neutron on it. There's 2 forms. It's funny how they label them. There's the S process and the R process. Sounds complicated, just slow and rapid. The slow one can take up to thousands of years, 1 capture at a time. When is that relevant? You'll see that is relevant in low mass stars in the last few thousands of years, the last part of their lives. You'll see that S process of neutron capturing underway, and that takes many, many years. Then there's rapid, or the R process of neutron capture, and that's usually in situations of high energy, massive explosions like supernova explosions and kilonova explosions, which we'll be talking about, where things are happening really, really quickly. And that's where you'll get a large nucleus called the seed nucleus. That's just a name given to it. And that will capture a neutron, but instead of waiting a few years before the next capture of a neutron, it'll up to 100 captures per second, really quick. There's just neutrons everywhere, there's a lot of energy, and it's capturing loads and loads of neutrons. So that's neutron capture, which we're going to be talking a lot about, and those are the two processes of which you capture. And you'll see the difference between the 2 has huge implications, which we'll be talking to. Then there's the concept of alpha capture. You now know what an alpha particle is. An alpha particle is a helium nucleus, 2 protons and 2 neutrons. To capture alpha particles, essentially that's a form of nuclear fusion. You need high temperatures to do that. You need at least temperatures of up to 100 million degrees to start bringing alpha particles together and start building up alpha particles from there. That's part of nuclear fusion, like your proton capture. So that's the main principles that we're going to be talking about. This is just a nice example here of some nuclear fusion. The idea behind it is you've got some deuterium here, which is a proton, and it's an isotope, so it's got a neutron with it here. There's some tritium, which is one proton and two neutrons. So two hydrogens, just different isotopes. They come together, they get fused under extreme conditions, extreme temperatures, and you create a helium nucleus sitting there. Now, the idea between nuclear fusion is that the product nucleus at the end of the equation is more stable, it's more tightly bound, more snug together. In other words, in a lower energy state. And that is expressed or seen by us as a huge release of energy and a drop in mass. The mass of the product is less than the mass of combined of the initial ingredients. And this brings up Einstein's famous equation, E equals mc square. What he was trying to say there is that energy and mass are one and the same. Just entities of different entities or things of the same, exactly the same thing. And he put that equation there. So the amount of energy in mass is equivalent to particular mass, c squared. C is the speed of light, which is a massive figure. So you square it, and it shows you that even just a small drop in mass gives rise to huge amounts of energy. And that's the whole thing behind nuclear fusion, is you get two small particles, fuse them together under extreme temperatures, create a product nucleus, which is a slightly smaller mass because it's just more stable, and huge amounts of energy are released. So that's the concept there of nuclear fusion. Yeah, and that usually involves, as we've just talked about, either capturing protons or bringing two protons together, or bringing alpha particles together and capturing them. So that's about capturing and building things up. Radioactivity, radioactive decay. You might think, isn't that things getting smaller? What's that got to do with nucleosynthesis, building up atoms? It's hugely important, hugely important. So radioactivity is where you get a large, unstable nucleus that's just big and bulky and unstable. And it emits energy and particles to try and put itself into a more stable state. And there's three ways it can do it. This one's labelled alpha decay, and that's whereby the large, big, bulky, unstable nucleus will emit an alpha particle, which we now know is a helium nucleus, so that's called alpha decay. There's beta decay, that's where a big, bulky nucleus spits out an electron. And what's going on there is that just as you've got a strong nuclear force, there's another force within the nucleus of atoms called the weak nuclear force. And the weak nuclear force, if the situation is unstable, if there's an unfavourable amount of ratio between protons and neutrons, the weak nuclear force will step in, if it's all unstable, and convert a neutron to a proton, or a proton to a neutron, can go between the two. When a neutron gets converted into a proton by the weak nuclear force, it releases a high speed, at high velocity electron, and that's known as beta decay. It's just the term that they've given to it, beta decay. And then there's a thing called gamma decay, and that's whereby you've got just big, bulky, uncomfortable, unhappy, unstable nucleus that wants to lower its energy state and become more stable. It's either emitted an alpha particle, or if it's emitted an electron and changed one of its protons to a neutron to a more stable state, but they're still not perfectly stable. To make that nucleus stable, often it will emit a high energy photon of light, a particle of light called a gamma ray will get emitted from it. And it's just getting rid of a little bit more excess energy to allow that nucleus to settle down into a more happier state. And that's called gamma decay. So that first one is mediated by the electromagnetic force for the alpha decay. You might say, oh, why is that? The reason it spat out that alpha particle is because it has got so big and bulky. Remember what I said about the strong nuclear force that holds neutrons and protons together? Short range. So as the nucleus gets bigger and bulkier, it starts losing control, if you will, of stuff in the peripheries. So We also know that you've got the electromagnetic force. We talked about that. Two positive protons are trying to repel one another, but the nuclear force is stronger. Well, you get further out into a big bulky nucleus, suddenly that electromagnetic force starts to overcome and be more powerful than that short range, strong nuclear force. So the electromagnetic force kicks in and kicks it out. And so that alpha radiation is mediated by the electromagnetic force, or alpha decay, and it's the weak nuclear force that's responsible for beta decay. These processes are really important in the formation of elements, as you will see. Okay, and I've just put an example up here. You've probably heard of uranium, mentioned the word uranium. Well, radioactive, absolutely. So here is a large uranium nucleus that's big, bulky, and unstable. So obviously in the peripheries out here, the strong nuclear force isn't strong enough to overpower the repulsion of the electromagnetic force, so it expels an alpha particle, so you get alpha radiation here, and create what we call it the parent nucleus, and you get your daughter nucleus here, which is thorium. That is a thorium. Thorium is just not perfectly stable yet, so just to de-excite itself, it then emits a gamma ray after that, and it becomes a more stable form of thorium. So that's a little bit of an example for you of what goes on with radioactive decay. And you can see from that example how suddenly you've made one element into another element. Okay, so that's a little bit about some atoms, particles, and principles. Let's talk about nucleosynthesis now. We'll start here. I thought I'm going to do the talk color-coded way, so let's talk about the Big Bang fusion. And so the Big Bang principle, it doesn't say anything about how the universe formed. It just purely says the universe was much, much smaller and much condensed and hotter than it is now. And slowly over time it's expanded and got cooler. In the first microsecond of the universe, it was so hot and tense, everything was just a sea of fundamental particles, just quarks and gluons flying around everywhere, and just massive sea of fundamental particles. Then from that first microsecond right up to perhaps 100, 200 seconds, so probably 2 or 3 minutes or so, protons were able to form and neutrons were able to form. So those quarks and gluons just flying around, suddenly the universe, they're just cool enough for that strong nuclear force to kick in, bring some quarks together to make protons and neutrons. And that was the state of the universe for 2 or 3 minutes. Then around 100 to 200 second mark, the protons and the neutrons were slowly able to join up together to create some hydrogen-2, which is deuterium. It's one proton and one neutron together to form an isotope of hydrogen. The temperature then was about 10 to the power of 12 degrees Kelvin, still extremely hot. And then about that 3 minute mark, right for the next 17 minutes, as long as the temperature kept below about 10 million degrees, 10 to the 9 Kelvin, you had hydrogen, and it could move on from then. Hydrogen could form helium, and some lithium, some beryllium formed. In other words, you started getting some nuclear fusion. More protons were building up, and you started getting some helium, lithium, and beryllium. Okay, so at the end of 20 minutes, the temperature had dropped enough in the universe whereby nuclear fusion could no longer carry on. It was too cool for that. But the result was about 75% hydrogen and about 24% helium, and just trace amounts of lithium. And you might say, well, where's the beryllium amongst that lot? Because if you look up in here, where's the beryllium? There's no big blue patches there, a little bit of lithium. Beryllium is very unstable, and within fractions of a second, beryllium will instantly go to lithium. So that little bit of beryllium that was made, it's converted back to lithium. So that was at the end of the first 20 minutes of nuclear fusion in the Big Bang state. These elements were still in a state of what we call plasma. Plasma means in a normal state, like here, all our atoms, as I showed you earlier on, a nucleus with electrons attracted to the nucleus, and you had this nice neutral atom. It was still too hot for that to happen, and still it was just a sea of electrons and atomic nuclei going around all over the place. And it wasn't until about 380,000 years later, when the universe had cooled down enough, where suddenly the electrons could get attracted towards the nucleus and stay in the orbits around the nucleus, and you get normal atoms. Okay, so that's Big Bang nucleosynthesis. Moving on now is the green. We're looking at dying low mass stars. Well, for starters, how do you define a low mass star? It's two main things. First of all, its mass, as a rule of thumb, is usually less than about 8 solar masses. That's how you tend to grade stars, by how much mass they've got. Our sun, of course, is 1 solar mass. So in other words, most stars under the mass of about 8 times our sun are considered low mass stars. But there's a far more important definition, that they finish their lives as a planetary nebula. And let's go up to here. You've probably all seen pictures like this. This is the Helix Nebula. It's a planetary nebula taken by the Hubble Space Telescope. And you see these beautiful pictures all around the place. This is what we call a planetary nebula. Nothing to do with planets. It's just a lot of names were wrongly given objects in the early days of astronomy before they understood things, and then they just kept the names for historical reasons. Yep. So there you go. That's called a planetary nebula, and that's how they define what a low mass star. Most stars under 8 solar masses end their lives as a planetary nebula, which we'll talk about in some more depth. This whole process of the dying process, as you'll see, of low mass stars, their last few years, and they're forming into this planetary nebula, is crucial for how they form new elements. And then, of course, you can see in this process, totally disperses them. Incidentally, as you can gather from what I've said, anything below 8 times the mass of our sun. So this is the destiny of our sun, by the way. Our sun will end up as what we call a white dwarf, which is a very hot, inner, dense core of carbon and oxygen sitting right in the middle there, that's blasting out ultraviolet light, and all these layers of gas and dust separating around it there. And that's all been illuminated by the ultraviolet light that's coming out of that hot, dense white dwarf in the middle. So that's the destiny of our sun. So that's how they define a low mass star. Less than 8 solar masses as a rule, but it's going to end its life like that. So let's talk more about them. Let's talk about the pathway of our sun. Our sun's what we call a main sequence star. Let's talk about the process it goes through to become a red giant, and then to finish up as a planetary nebula, and the elements that form in the process. All stars, and our sun's going through this at the moment, the first 90% of their lives is in a relatively stable state known as the main sequence. And I'll show you shortly, by definition, they're fusing hydrogen into helium in their cores. They then go through a red giant phase where they start fusing hydrogen to helium. You get nuclear fusion in the core and in these outer shells, but I'm going to show you all that. So let's start with the main sequence. So that's our sun, is in the middle of the main sequence phase. And what's going on here is that once a star is formed, the inward pressure of its mass creates the gravity, increases the force, the inward force, and slowly the pressure and temperatures in the central core region of the star will increase because of gravity and get hotter and hotter, whereby hydrogen fusion can start fusing into helium, and you get nuclear fusion going on. That nuclear fusion, as I showed you early on, produces large, huge amounts of energy, and it's that outward energy being released by nuclear fusion that then balances that inward crushing force of gravity, and it keeps the star in what we call a state of hydroequilibrium, just keeps it nice and stable. And all stars spend 90% of their lives in this nice stable state. Our sun's about halfway through this at the moment. The temperature in our sun is about 15 million degrees. That's not quite energetic enough to drive 2 protons together, to overcome that electromagnetic force. It's not quite hot enough. Who can tell me what assistance that the laws of nature helps out the middle of our sun? Quantum tunneling, in comes quantum physics, quantum tunneling. So like I said, just with plain physics, just 15 million degrees is not sufficient to bring 2 protons together to overcome that repulsion of electromagnetic forces. But quantum physics, which is hugely successful, overrides that. And on very small scales, it says that the position of particles is not a certainty, it's only a probability. and it can't say for definitely this pointer is sitting right here. There's a very, very low probability, but it's not impossible that it could actually be over here 1 minute and over here the next, and so on. And so with particles. So the position of a particle is not a certainty, it's a probability. And there's just a small chance, and they often use this hill to climb over. This represents the resistance against electromagnetic forces. It's like bringing two equal sides of a magnet, two north poles together. They resist one another. It gets closer you get, gets higher and higher and higher. And the idea is that if the strong nuclear force can kick in, bang, it snaps it in. But quantum physics says, yeah, your particle, your proton might be here, and most likely it'll always be there, but there's a tiny chance it might just suddenly appear over here. And they do the calculations, and they said accordingly, a small percentage of the hydrogen should quantum tunnel through to the other side, whereby the strong nuclear force can grab it and snatch it and hold it in place. And indeed, the calculations match perfectly accordingly to how much hydrogen is there, how much hydrogen should be allowed through with quantum tunneling, and how much energy should be released. The equations work perfectly. So it's called quantum tunneling, and that's what allows nuclear fusion to overcome the electromagnetic force. As I mentioned too before, there are two main processes by you can bring a series of protons, hydrogen nuclei together to form helium. Proton-proton chain and the CNO. That stands for carbon, nitrogen, oxygen cycle. There's a lot more detail to it than this. There's about 4 main different pathways of the proton-proton chain. But the main one here, just very briefly, is you're actually getting 6 of them, but the net product is you get 4 protons, 2 of them change into neutrons, and they all get brought together to form a helium nucleus. That is far more stable state with less mass than starting out with, and huge amounts of energy is released. That's in the handout and that, but that's the proton-proton chain. And like I said, there's about 4 different variations of that. There's one, this particular one is about 85% of it. Then there's another way called the carbon, nitrogen, oxygen cycle, whereby the carbon, nitrogen, oxygen act like catalysts, where they enter a reaction, facilitate a reaction, and come out exactly as they entered it again, just like a catalyst would. So there's a series of equations. If you've got carbon, like you've got substance in your star from previous generations of stars, you add carbon in there, you add some nitrogen in there, and oxygen, it all comes through. The carbon and nitrogen, oxygen comes out at the other end, but it speeds up the whole process of converting hydrogen to helium. Now, why am I going through all of that? Is because it is important to know that these are the 2 main ways for hydrogen fusion to helium, and that is by far the commonest reaction that's going on in the universe right now, is that the CNO cycle is far more efficient, pumps out far more energy for any given temperature, but it doesn't kick in until about 12 million degrees. Our sun at its core is about 15 million degrees, and you can see predominantly it's the proton-proton chain. But as you get larger and larger stars have more mass, so they've got more gravity pulling in them, so their cores have higher temperatures, you get increasingly contribution of the CNO cycle fusing hydrogen to helium, which is far more effective and efficient. And that's one of the reasons why big massive stars tend to burn up their hydrogen so much quicker, be more efficient, blasting out more energy, and race through their lives a lot quicker. It's not only because they've got more gravity going on with pressures, but it's also because they tend to burn up with the CNO cycle. Yeah, and that's the implication of that. But as you can see, it's the proton-proton chain that dominates nuclear fusion in our sun. Okay, now, like all good things in life never last. So in the core of that main sequence star, eventually it runs out of hydrogen. In the core, all the hydrogen in the core is all being fused together to form helium. So the core just fills up with helium. It's not hot enough yet to bring helium together into the next stage, which is carbon. So the helium just sits there in an inert stage. Nuclear fusion in the core essentially comes to a halt. However, a couple of comments. One is, it's still hot enough for a shell of hydrogen to continue burning into helium around that inert helium core. And it's that shell of hydrogen burning that pushes the outer layers of the stars outward and makes it swell up into a red giant. It's purely, that's what's going on. So that's why it's a giant. Why is it red? Well, you've got roughly the same amount of energy going on getting pumped out, but suddenly you've got a larger surface area to spread that energy over. What happens to a hot flame when you wind it down? It turns a bit red, doesn't it? You know, a hot flame's really hot's blue or white, and your fireplace, like when your fire's running out or your flame's a lot lower, it's a red colour, isn't it? So hence it's a red giant.
That explains why blue stars are typically hotter than stars like our sun.
Correct. Now, the other thing that here is that because you've got no nuclear fusion going on in this core, you haven't got that outward pressure of the shell's enough to push the star out, but it's not sufficient to hold the star up against gravity. So you've got this increasing force that continues down onto the core, and the pressure and the temperatures in the core start rising because you've got no nuclear fusion going on in there, but you've still got all this mass centering in on the core. Moving along, we're going to move on. I just wanted to point out now, the red giant now breaks into two phases. The red giant branch, this all comes from a thing which we'll do a whole talk on called the Hertzsprung-Russell diagram, but we won't worry about that tonight. And then called the AGB branch, or the asymptotic giant branch. So there's just two phases that these red giants will go through. So the first, the red giant branch, that core of inert helium where there's no fusion going on, and you get all the star crushing on it, the temperature rises higher and higher and higher until it gets to 100 million degrees, and that then is sufficiently hot enough to start ramming helium nuclei together, or alpha particles, ramming them together to create carbon. They call it the triple alpha process. You might say, well, hey, you got beryllium in the middle. Yeah, two heliums initially form beryllium, but what did I say about beryllium? Really, really unstable. Within a fraction of a second, it just goes to lithium. But it's hot enough at 100 million degrees, almost as instantly as you've done the beryllium, that can quickly throw in another alpha particle to create carbon. So it happens really, really quickly, and that's why you need such huge temperature. You've got this barrier to overcome. Every time you bring two alpha particles together, they form beryllium, and beryllium just disintegrates again. So you've got to be on the mark, 100 million degrees, and ram that third one in. So it's called a triple alpha process. So that continues, and eventually all the helium gets used up, and you've just got a core of carbon. But 100 million degrees is sufficient to make carbon, but it's not sufficient to do anything further from there. So at this stage, you've got your inert carbon, which is not hot enough for nuclear fusion. You've got your shell of helium. Shell, once again, is hot on the outside just to have a little shell of helium burning away there. And then outside of there, you've got your hydrogen shell. So you've got two shells of fusion going on, so that pushes the star out a little bit more, really, to keep that propped up with a nice big red giant, and it gets larger and larger. But that inert core, so what's happening? You've still got the same amount of mass, though, that's pressing down to the core, so the core temperatures just continue to rise and rise again. And at that stage, your red giant branch turns into what we call an early AGB, or asymptotic giant branch. And that's where the temperatures then, you can add another alpha particle, so there's the alpha capturing, gets added to carbon, and you start getting some oxygen added in. So the core now is forming into carbon and oxygen. That core will eventually become our white dwarf as we go forward, that you saw before in the middle of that planetary nebula. So that's the early stages, and we're just going to go ahead a little bit here. As I mentioned, so here's your white dwarf. That's that sitting right in the middle. That's going to be our sun one day. And that's just a hot, dense core of carbon and oxygen. And that's how it got there. So there you go. Stars up to 8 solar masses. They're not big enough. You might say, why don't we move further, guys? We leave that to the bigger stars. Stars 8 solar masses or below only have enough gravity to come in with the forces to create enough temperatures to convert hydrogen to helium to carbon and then oxygen. And that's the end of the line for what goes on at the core. Now, so that jumped ahead a little bit just to show you what happens to the core eventually. But the late stage asymptotic giant branch of these red dwarfs, and this is important, here's your core of inert carbon and oxygen. That slowly the temperatures are continuing to rise. You've got the shell here of helium that's burning away. You've got your hydrogen shell here, and you've got your cooler outer layers. This is not the scale. This area here is just a tiny fraction. You could shrink that in probably much smaller than my little dot there. But they've just made it much larger just to be illustrative. But this green spot here, this region in here is hot enough where it's right between the two. It's not quite hot enough. It's full of helium. The hydrogen's all burning here. The helium's burning here. And this is almost like a no man's land. It's full of helium, but it's not hot. It's just further enough out. It's not hot enough for helium fusion to occur. But what does happen as the star contracts down, it does heat up and eventually it bursts. Nuclear fusion, helium fusion does kick in, and it just, when it pushes the stars out, called a thermal pulse. And as it pushes out, it eventually expands. What happens when you expand? You cool down. And it cools down, helium fusion stops, and it starts shrinking back down again. And it's just a continuous cycle of nuclear fusion kicking in and out in this no man's land here of just straight helium layer that's not always burning. That creates these thermal pulses. These thermal pulses makes the whole star pulse. But importantly, they drive these big convection cells of the outer layers here that start churning over, like boiling water or your porridge in the morning, just churning it over. And it's all driven by these thermal pulses that are going on in the inside. The relevance of that is these big convection cells that are moving through. They're churning up all the contents of the star, and critically, they're bringing the carbon up from down near the core regions that's newly been produced, and they're bringing it up to the surface of the star, into those outer layers of the star. That's crucial what's going on in here. Then that's called, by the way, called dredging, that process. But the other important thing is that as the carbon is starting to move up, you start getting, there's a lot of alpha particles in there as process as well, but you start getting some S process. Remember we talked about the neutron capturing, the slow process happens in dying stars? This whole process of dredging, of material being dragged up with these pulses and creating convection zones, really stirring up the contents of the star. This is happening over years and thousands of years. It's not something that happens very quickly. It's slowly churning away. And in that process, from previous generations of stars and newly made carbon, but also some neon from previous generations of stars, they're combining with alpha particles amongst there as well. It's just hot enough for a little bit of that going on deep down. And those reactions are creating an excess of neutrons. So suddenly in these outer layers, you've got loads and loads of neutrons going on there. You've got some alpha particles as well, but it's prime for all these things that are coming up from below, the carbon and light, to capture some neutrons by the slow process. It's happening over thousands of years. Just neutrons are slowly being seeded onto these nuclei as they start working their way up. Typically, it's iron is the commonest one, is the nucleus that gets added to. So here it is here, the S process neutron captures mechanism. And the relevance of this being the slow process taking thousands of years, beta decay occurs within a fraction of a second. It kicks in very quickly. So it's got time. These captures a neutron, and it might be a few years before it captures another neutron. That neutron sits there, and that neutron becomes unstable. So it's got time before it grabs the next neutron for beta decay. Quietly, the weak nuclear force converts that neutron into a proton. So you can see where I'm heading with this. What happens when you change proton numbers? You're changing new elements. You're building up new elements. So it's this slow process of capturing more and more neutrons as the whole tuning process is going on. And because it's happening slowly, there's plenty of time there for the weak nuclear force to convert a lot of these neutrons, quietly convert them into protons, new elements. Like I said, iron nuclei, where does that come from? Previous generations of stars. Every star is a product of a previous generation of stars. And that's usually the main seed. It's the iron that captures these neutrons slowly through the S process, allowing time for the weak nuclear force to convert the neutrons into protons and build up. And here it is here in green. I've highlighted them here. So it's from strontium right through there, all the green here, right through to lutetium via lead. So all those elements there are made, and as our star goes through this, our star in its latter few thousands of years of its life, will start expanding out. It'll have these pulsations going on, thermal pulsations, that will drive convection cells working away, churning stuff up, and iron that's already in the sun will then capture neutrons, which will then slowly convert into protons, and will make all these elements here that are in green. So that's what goes on when they talk about dying low mass stars. That's the process they're referring to. Slowly, of course, what happens is that outward thermal pulses just continues, and over tens of thousands of years the star gets less and less stable, and all the outer layers starts shedding themselves off into these lovely huge, you're talking many light years across here. These can last for 20 or 30,000 years quite happily, and like I said, there's your core of your low mass star in the middle. It's just hot carbon and oxygen emitting ultraviolet light, just illuminating all your carbon and all your other products, all those elements that were in green before, they're all out there being dispersed through the galaxy by these planetary nebula. Let's have a look. Now, that's a bit of the theory. Well, where are these things out there in the sky? The Helix Nebula that we saw up here, that is in the constellation Aquarius. That's quite high in the sky. It's with a good telescope and a dark sky, you can quite happily see that. It's in Aquarius. The spring months, the best for that, September through to November, the constellation Aquarius. I can see it happily with my telescope from home. So you can see the stuff out there. And it's good, next time you do look up there, you know exactly what's going on. You think, okay, that's the product of a low mass dying star. That's slow neutron capture has happened and beta decay has turned them into protons. Here is Aldebaran. That's a nice red giant in the sky. That's over in December, January, February, the southern hemisphere's summer months. That's in the constellation Taurus. Aldebaran is in Taurus, the constellation Taurus, which is the bull. And Aldebaran in Arabic means eye of the bull. And it's a nice red giant sitting right there. So that's a very relatively close red giant and planetary nebula that you can see with your own telescope at home. That's producing all these things in green here from dying, the last gasps of a low mass star. Let's move on now. We've talked about white dwarfs very briefly. Let's talk about white dwarfs that produce all the silicon to zinc elements. So you now know what a white dwarf is. You might think, well, that's the end of the line, is it? No, it's not. The party's not over yet, guys. These white dwarfs certainly can carry on doing some interesting stuff, and they can be highly explosive, which we'll talk about, and create more elements. Our sun is a bit of an exception in terms of just out on its own. A lot of, over 50% of star systems actually have 2, 3, 4, sometimes more stars, like in a binary system, just 2 stars going around one another. If you get a white dwarf that's in a binary system, that its partner, companion star, is a little bit younger, so it hasn't quite reached the white dwarf stage yet, but it's a red giant, so it's really puffed out and it's quite unstable, you can get a lot of that unstable outer material from the red giant can overflow and get siphoned and form a big disk around the white dwarf, like that, and slowly builds up onto the white dwarf. If the white dwarf reaches a certain temperature, it explodes. They've worked it out. A white dwarf, by the way, is about the mass of our sun, squashed into something the size of our Earth, to give you an idea. It's fairly dense. It becomes extremely unstable and explodes when its mass builds up to about 1.4 solar masses. And here it is here. If it gets greater than 1.4 solar masses because of siphoning too much material, the carbon ignites with fusion, and within about a second, the whole thing is just torn apart. And I've got a little video here just to go there. Yeah, and of note, in that massive explosion, there are 3 types of reactions that are going on that's forging new elements. It is explosive. These are the most energetic and explosive events in the universe. They typically they cause what they call type 1a supernovas, and they're usually what astronomers use to measure distances to faraway galaxies. They are so bright. So there's nuclear fusion going on in there. Carbon gets brought together to form neon, sodium, magnesium. Oxygen gets fused together to form silicon, phosphorus, sulfur. You've also got neutron capture. You've got alpha particles being captured there as well. Neutron capture. In such a violent event, what would you expect the neutron capture to be? S process or R process? R process, rapid. It's just huge, within seconds. Before you had the luxury of thousands of years, it was the slow process. Neutrons are getting tacked on really, really quickly. So you're getting all those in there as well. And then you get a little bit of radioactive. You get nickel will radioactively drop down to cobalt, and then via radioactive decay go down to iron. So you've got three different processes going on here. Here's my video. So there's your big red giant, which is siphoning material because the white dwarf's got a huge gravitational field because it's compact and dense. An accretion disk is forming around it, and it's slowly building more and more material, which is dumping onto the white dwarf. And slowly the white dwarf gets up to a mass of about 1.4 solar masses, and whammo, it completely rips itself apart within a second. Type 1a supernova. And a lot of elements get made in that time. So where is that related to in the night sky? Our nearest white dwarf would be, you're probably familiar with Sirius, the star in the night sky, the dog star. Sirius is actually two stars. It's in a binary system. We see the main star, it's a main sequence star, Sirius A, but it has a companion, and its companion is a white dwarf, Sirius B.
But it's so dim we can't see it.
Correct. You can't see it with your unaided eye. Correct. So that's Sirius. So that's our nearest white dwarf, 8.6 light years away. That's in Canis Major, being the dog star. Sirius A, you might say, oh, could that be a type 1a supernova so close to us? I was going to say unfortunately. Fortunately not. Sirius A is about 2 solar masses, so it's going to go into a red giant, yes, but the separation between the two is too far apart. If they were a lot closer together, yes, it could siphon material onto the white dwarf, but the distance between them is too far apart, so there's no potential type 1a supernova happening there. But I put that in there so you can look up at the night sky and you see Sirius. There's a white dwarf there. You know now where there's a red giant, Aldebaran. You know where there's a planetary nebula to look at. So that's exploding white dwarfs. Extremely bright thermonuclear reactions, and they produce what we call the iron peak material, because here's your iron here, and they call it the iron peak because it's all the elements here around iron that tends to form. So they are all produced in those massive explosions through nuclear fusion and the R process of neutron capture. Okay, so let's move on to, we've done low mass stars, how they die and then slowly puff out, and how their inner core can explode if they've got a companion. So let's look at stars over the 8 solar masses have got enough mass to generate enough gravity to create enough inward force. So once you've put carbon into oxygen, where stars less than 8 solar masses just into the line, these stars have got enough gravity to keep driving down, just ramping up those pressures and temperatures in the core. And once again, it's called the alpha process because you're adding alpha particles. So you can see why we talked early on about the whole concept of alpha particles, helium nuclei. So you get carbon, you add an alpha particle, you get oxygen, and you just keep building up, adding more alpha particles till you get neon, then you get magnesium, silicon, sulfur, and you start building up more and more. And as this process happens, more and more energy gets released, and the star just gets bigger and bigger and bigger, and becomes what they call a red supergiant at this stage. So you get higher and higher elements until iron. Okay. This is what the star looks like, the red supergiant looks like, and this is, you can see this is a better diagram. It's still not to scale, but it illustrates better how the core with all these shells around. It's in the tiny bit. You tend to blow it out so it's easier to see. So here you've got your iron that's just formed, your inert iron. Then you've got all these different layers. They often call it the onion model because it looks like an onion with onion layers. But each time a new element's formed, and then it runs out, and it sits there inert for a while. It starts burning in a shell, and then the temperature slowly rises, and the next element starts forging, and eventually that comes to a halt, forms a shell. So you get these multiple shells in the order at which these new heavier elements are formed. And it's called the onion shell. It looks like layers of an onion inside the core. Yeah, so what happens when you get to iron? Up till now, every time you've brought two nuclei together to create a bigger nucleus, the reaction is what we call exothermic, releasing energy, because each time the nucleus is that little bit more stable, so it releases energy and mass and giving it out, and that props the star up. But suddenly, with this, iron is what we call endothermic. Iron is really snug, tightly bound, and very, very stable. So to break iron apart, you actually need to put energy in. You don't give out energy. So essentially, the whole star comes to a halt, and the entire, within a fraction of a second, I've actually put here, these are the stages by, there's another little principle. How for each stage gets shorter and shorter and shorter. This is for a 25 solar mass star. So you've got 7 million years here in a main sequence. Notice you write down silicon converting to iron within 1 day. That core collapse, a quarter of a second. You produce iron, bang, end of the road. It doesn't just sit there. Within a quarter of a second, blink of your eyelid, bang, the whole thing, that core just completely collapses. And a few things happen. Those temperatures, you're talking up to about 10 billion degrees, huge temperatures. And at 10 billion degrees, you suddenly get a mass of intense gamma radiation. That's high energy, extremely high energy photons of light. And it instantly just shreds all the iron that took all those years and thousands of years to slowly build up and create iron. That just gets dismantled and shredded into alpha particles within a fraction of a second. It's all been undone. All the iron and all the lead up to iron has completely gone into alpha particles. The second thing that goes on is because huge forces involved, so you've got all these alpha particles can create, you've got protons and electrons flying in all directions. Is under the forces, the protons and the electrons get rammed together to create neutrons. And in that process, these little particles, little tiny ghostly particles called neutrinos get produced in the process as well. And that's the equation there. Proton plus electron forms a neutron and a neutrino. And that has big implications as well, because that aids the whole process. The core starts collapsing down, as I said, but what accelerates it is these neutrinos, they tend not to react with particles. There's millions of them going through your finger every second of the day. Just you don't know about them. They just zip through things. They're very, very tiny and ghostly particles, but they do carry heat away with them. So they move at lightning speed, literally, because they don't interact with matter, so they just zip out, but they take huge amounts of heat out with them. That has two implications. The first one is you've got this core collapse going on, suddenly all the heat's taken out of it as well, and that accelerates the collapse. So the collapse happens almost instantly. Let's now consider the core, split it up to an inner core and an outer core. We've just talked about a core up till now. The inner core collapses faster, and it meets some resistance. All the neutrons just get rammed together, and it's almost like just a brick wall, a solid surface of solid neutrons. Most stars, that's going to end up as a neutron star, but that offers a bit of a resistance like a wall. Then you've got the outer core that's behind it coming in, collapsing in onto it, and that starts rebounding off that and starts driving an outward force. So you've got the outer core meets the resistance of the inner core and starts rebounding. Meanwhile, and that's all exaggerated by the outward flux of heated neutrinos, you've also got all the outer layers. Suddenly, the core's just started collapsing. All this with gravity, all the outer layers of the star start coming in as well. This is bound. That hits the outer core that's starting to rebound off the inner core. That hits them as well. You've also got, amongst all that as well, you've got the outer layers hit the rebounding outer core, and then they rebound off that again. So you've got rebound going on rebound. You've got the outer layers rebounding off the outer core. That's already itself rebounding off the inner core. And I've got a little experiment to show you, demonstration shortly to show you that. But accelerating that and even making it more powerful, is where I mentioned these neutrinos just taking the heat out really quickly. That's creating thermal pulses, which adds to the whole explosive effect of a supernova explosion. So all of this rebound, you've got this highly energetic supernova explosion going on. And with that explosion, you get some nuclear fusion going on within a few seconds. This is, by the way, not the main way that elements are formed in a explosion, but you've got nuclear fusion going on. You've got huge, massive outward rebound forces going on, driven by the neutrinos carrying energy out, and the rebounding outer material rebounding off the outer core that's rebounding off the solid resistant inner core. And you're creating all these elements here that I've highlighted in here. So these supernova explosions through nuclear fusion, within the space of a few seconds, all these elements here get formed. Now, I want to demonstrate something to you here. This is, you might say, well, just a bit of rebound, so big deal. How explosive can a bit of rebound possibly be? I want to show you something to consider. Let's just say, for argument's sake, this is the outer core rebounding off the inner core. Okay, let's just see how much, bounce, yay high. And let's just consider that this is the outer layers of the star meeting the outer core and rebounding off just on its own. Bounces yay big. You watch what happens now when something rebounds off something else that's already rebounding. Let's see if I can do this straight up and down. Whoa. Look at that. That's the principle of compound rebound. God, let's do that again. I have been known. I took Brenton's one of his ceiling tiles out once. I better. A new ceiling. But there you go. Look at that. So that is one of the key principles why supernova explosions are so explosive. You've got rebound on rebound. The outer material is rebounding off the outer core, which is already rebounding off the inner core. And that's what's going on. What did I put with my little thing? Here it is. So you won't forget that. Well, the ceiling won't. Another important part of that's going on is neutron capture. Our friend neutron capture is also going on as well. This is a fertile ground. Suddenly you've got all these explosions going on, all this nuclear fusion going on. But what did I say earlier on? You've got all these neutrons being formed. So you've got an explosive environment that's really rich in neutrons that are being formed. So also you're building up heavy nuclei through neutron capturing. And like I said, it's a no-brainer. Is it the S process or the R process? It's an explosive environment. It's the R process. So within seconds, this is all going on. Now, what is as I mentioned before, it has implications, the slow. You saw the slow process, or S process, the implications of that is it happens slowly. So a neutron's got time to attach itself to a nuclei, and it's got time to convert to a proton and create a new element before the next one comes along. Beta decay can change the neutron to a proton. But with rapid or R process neutron capture, and you're talking up to 100 per second, you're grabbing one neutron and you're grabbing another neutron before the beta decay's even had a chance to even think about it yet. So slowly you get this atomic nuclei that's building up more and more neutrons really, really quickly. Neutron, building and building up really quickly. The beta decay hasn't had a chance to kick in. But slowly with time, the neutron density drops, beta decay kicks in, and the R process comes to a bit of a halt, usually within seconds. But by that stage, you've already got a nucleus just full of neutrons that then slowly start changing to protons. So you can see another whole family of heavy elements can get formed in that environment. And here we go here. These are all the remaining elements that get formed via the R process neutron capture in a supernova, core collapse supernova. So where are these in the sky? Betelgeuse. Betelgeuse is a red supergiant. So it's a massive star. It's gone through the main sequence. It's in its final stages of its life. It's slowly building up those heavy elements. And one day, soon, it's going to hit iron, and within a quarter of a second, the whole lot's going to collapse, and it's going to be a massive supernova explosion. Soon, in astronomy language, is sometime in the next 100,000 years. So, but it's still exciting. So that's when you look up into the sky, Betelgeuse, it's a red supergiant. It's going to go supernova. So you can think about all the elements that are going on inside it right now and what elements are going to be formed. In terms of a supernova remnant, like here, this is the Crab Nebula, also known as M1. And this is in Taurus. So we looked at Aldebaran was here. We looked at that. We looked at Betelgeuse. If you draw a bit of a triangle down, it's really faint. I've seen it with my telescope at home, but it is really faint. It's known as Messier object number 1. You can see the remnants of the Crab Nebula. That was a red supergiant that exploded, went supernova in 1054, was well documented. And you look in that exact spot, I believe there's a neutron star right in the middle. But you can see the Crab Nebula. I put that here because it was just the other day someone showed me. The Hubble Space Telescope has got online, got some images from 1999. And then 25 years later, in 2024, it took some more images and matched up the right angular size and stuff. And you can see the two images, you play them backwards and forwards, and you can see the expansion of how far it's gone out in that 25 years. So there you go. So there's a red supergiant in the sky that you can see, and the Crab Nebula, a supernova remnant that you can see. So it's not all theory, you can see the stuff out there. So that is exploding massive stars. Let's move on to merging neutron stars. And we talk about all these different star groups, and I want to introduce you to where neutron stars fit in amongst all of this. So this is just a very summary. This is in your handout, this diagram. This is just roughly, so you start here in the main, all stars start in the main sequence, burning hydrogen to helium. Then they're split into low mass stars or massive stars, and it's dictated by which pathway they go down. So the low stars go into that red giant, fusing helium into oxygen and carbon rather into oxygen. Then they puffed out those thermal pulses, they puffed out into planetary nebula, and then they formed into that white dwarf, and that's less, as a rule of thumb, less than 8 solar masses. Then with the much more massive stars, greater than 8 solar masses, they form into these red supergiants. They get really, really large because they're forming that onion ring. There's shell after shell after shell of hydrogen and helium and carbon and oxygen fusion going on there, pushes them out. They then create iron. Iron can't fuse together, what creates energy to do so, explodes in a supernova explosion. Now, what happens then? Stars between 8 and 20 solar masses, as a rule, when that inner core gets halted. All those neutrons form, and gravity can't overcome that anymore. So it remains there, and it's called a neutron star because it's really densely compact with neutrons.
Way more than the white dwarf.
Way more than a white dwarf, yeah. Now, stars greater than roughly 20 solar masses, they have much more gravity, inward force of gravity, and often they will overcome the resistant forces of neutrons all packed together, neutron stars, and they crush it down any further and create a black hole. So black holes are essentially stellar cores, dead stellar corpses, if you will, of massive stars greater than 20 solar masses, roughly, and you get a black hole that gets created. So that I just wanted to put this diagram in here just to put it in perspective where neutron stars and black holes fit in and the whole evolutionary process. So let's talk about neutron stars. So this is those inner cores that just settle down, stabilize, full of neutrons. And as I mentioned, most stars are in some sort of companion system, usually a binary system. And if you get 2 neutron stars in a companion system, they will often merge with a massive explosion called a kilonova. There's a type of explosion called a nova. It's a long story, but a kilonova is one that's about 1,000 times brighter. They detect them through gravitational waves and then can look at them more with X-ray telescopes and get an idea of what's going on. But as you can imagine, this is a fertile environment. This is ripe for creating new elements. You've got 2 bodies that are rich in neutrons that have just been slammed together in a highly explosive event. Hello, neutron capture, our process in full swing. And this is really the main form of nucleosynthesis, or creation of elements made through nuclear reactions and neutron mergers. It's the R process, neutron capture. You might say, well, where do the seeds come from? It's usually iron. Around the neutron stars usually have a crust around them that's very rich in iron, and it's that iron in the crust around neutron stars that forms the seed nucleus that then captures the neutrons. Beta decay, slowly, the R process, so you're gathering loads and loads and loads of neutrons really quickly. Then beta decay starts kicking in, and you start getting more stable, heavy elements forming. That's where your gold and silver or your fine jewellery comes from, merging neutron stars. Okay, so that's them there. And then finally, cosmic ray fission, the light elements, also known as spallation. And that's where you get an intergalactic space or interstellar space, and you get really high velocity protons, hydrogen nuclei, and they will slam in possibly to some carbon, nitrogen, and oxygen, and they split it up. They create alpha particles and further hydrogens. But you get your helium-3, an isotope of helium, you get lithium and beryllium and boron from this process in space. So you can see it at here, these ones here are formed. Okay, so I think it's time to slowly wrap up. It's been a lot of information. It's that and much more is in your handout, so you can just quietly read through. So let's go over some key points. Just first of all the hydrogen that in the universe today came from that primordial hydrogen formed in the Big Bang. You might say, well, how much helium? Because helium gets made inside stars during that main sequence phase in all stars. About 10 to 15% of the helium in the universe is made inside stars. About 85 to 90% of it is still primordial helium from the Big Bang. The nucleosynthesis that's occurring since the Big Bang involves three main astrophysical processes. Let's make it really straightforward and simple. One, nuclear fusion. That happens inside all stars, big and small, during explosive events like supernova explosions. Huge, powerful pressures and temperatures, overcoming electromagnetic forces with a little bit of help of quantum mechanics, with tunneling, slams things together, overcomes the electromagnetic force to create larger nuclei. Neutron capture, capturing neutrons, either the S process, doing it slowly, that occurs inside dying low mass stars, in particular those AGBs, those asymptotic giant branch stars. And the idea behind that, it happens slowly over many years, so the beta decay's got plenty of time to kick in, decide whether a nucleus is stable or not, and whether it wants to convert a neutron into a proton, or via the R rapid process and explosive events, supernova and kilonova. And I highlighted there, underlined kilonova, because it's actually, kilonova is by far the commonest environment where you get much more than the supernova explosions, where you get the R process going on. And then you've got radioactive decay. You can get alpha decay with the alpha particle getting spit out, large, big, bulky, unstable nucleus. It's spitting out an alpha particle because the strong nuclear force can no longer keep hold of everything, so electromagnetic force repels it. Beta decay, that's when the weak nuclear force converts a neutron into a proton, throws out an electron in the process, and then that gamma decay with a photon of light, high energy light gets emitted to create just that little bit more stable nucleus. So that involves, large unstable nuclei. So it comes down to those three processes essentially. So Carl Sagan was right. We are made of star stuff. Thank you.